In the name of Allah, the most gracious, the most merciful. As Prophet Muhammad, peace be upon him, narrated, if anyone travels on a road in search of knowledge, Almighty Allah will cause him to travel on one of the roads of paradise. Hello everyone, this is Dr. Tariq Masood. Thank you very much for watching my videos and your exceptional support to make this channel a grand success. We are a partner and family. Please subscribe and share our channel if you haven't done so far. We as a team can work together to convert challenges into opportunities and opportunity into success stories. These success stories can be monetized into value addition. Thank you very much for your precious time. Okay, as we have promised to deliver 100 lectures, now today we are going to discuss my lecture number 5th. Before my lecture, I used to read a Quranic verse. Rabbi Shrahli Sadri Wayassarli Amri Wahlul Uqdatam min Lisani Yaqfa Qawli Rabbi Zidni Ilma. Okay, now from my next slide, I will brief about my acknowledgement, the professor, the faculty member who contributed and supported me on my smart gate operation control challenges, and later on I will give you key takeaway points and highlights, and then I will run a complete trail on my lecture number 5th. This is my acknowledgement page. I pay my special gratitude all faculty members, in particularly Professor Dr. R.K. Agarwal, former Director of Center of Sustainable Power Distribution, University of Abbottabad. He was my supervisor. I worked with him more than 12 years. Professor Dr. Abdulati Adris Alaid, a former APRI Senior Technology Manager, California, USA. So he was my mentor and external supervisor. Unfortunately, he passed away in 2016. Almighty Allah bless him, highest place in Jannah. Professor Dr. Muhammad Afzal Haq, Professor Dr. Nad Mohan, Professor Dr. Florin Pamtu, Professor Dr. Muhammad Jambal, Professor Dr. B.S. Chaudhary, Professor Dr. Nasir Imadi, Professor Dr. Akhtar Kalam, Head of Smart Technology from Victoria University, Australia, Professor Dr. Suhail Aftab Qureshi, former Dean UT Lahore, Professor Dr. D.P. Kotari, Professor Dr. Abdul Jabbar, CO ADP, Pakistan. Okay, smart grid operations and control challenges introduction, lecture number 5th here. So in my earlier lecture, what we discussed so far, just a slight recap. We have discussed electricity required for our civilization, electric power functionality, energy efficiency from generation to consumption, ultimate goal of smart grid. We discussed power system infrastructure development, power system complexity, power system limitations, and reactive power significance and management. We have also discussed reactive power management, how to produce, challenge to manage reactive power, balanced reactive power, challenge at AC power system. In lecture number 4, we have discussed dealing with thermal limit, increase transmission conductor current carrying capacity, DTCR, dynamic thermal circuit rating technology. Okay, so on my next slide, I will give you my future plan 100 lecture program, and then I will give you my key takeaway points, and then we'll run a complete trail on my lecture number 5th. This is my 100 lecture plan. These will be delivered within 8 to 9 months. Okay, what basically my plan? So I will give you a brief about understanding a fixed concept technology. What is a concept? Then we will discuss a power semiconductor devices, voltage source converter, self and line commutated current source converters, SVC and STATCOM operations, static series compensators, static voltage and phase angle regulators, combined compensator UPFC, special purpose fax devices of controllers, and application. We will discuss few example. The fax devices already implemented in United States. What is the ultimate goal of fax technology or smart grid? Shaping the global energy delivery, fax on resolving gridlocks and delivering clean and poor energy. That is the plan. In order to deliver, shape the global energy delivery, faxed on resolving grid, delivering clean and pure energy. Okay, on my next slide, I'm going to give you a key takeaway points. Okay, key takeaway points, lecture number 5. Today we will discuss first generation compensator, mechanical switched capacitor reactors. Number 2, we'll discuss power electronics based second generation compensator, SVC, TCR, TSSC, and we'll discuss a third generation compensator, STATCOM, SSC, UPFC. On my next slide, I will give you highlights what we have discussed lecture number 1, 2, 3, 4, and then we will run a complete trail on first, second, and third generation compensator. Okay, I express my deep gratitude to all faculty members, students, and leadership, in particular VCs and deans of the universities as listed here. UET Lahore, NFC Multan, RCT Gujranwala, Mehran, NED Habib, NUST, International Research, Karachi Electric, Distinguished Lecture, IEEE Qatar Sections, University of District Columbia, University of Texas Arlington, Texas Tech University, University of Bath, Qatar University, Texas A&M Qatar, University of Granada, University of Salamanca, COMSATS Abbottabad, City University Peshawar. Okay, as we have discussed lecture number 1 and 2, just we are going to give a highlight what we have discussed earlier. Basically, what are the key elements? Why we need a smart grid? Smart grid evolutionary development, fundamental approach for smart grid operation and challenges. So technically, what are the driving factors which we need to consider in order to deliver the required results? First boundary is called the grid condition and requirements. This is the first operating boundaries we need to understand and to determine its criticalities. So what are these criticalities? Variable power supply, integration of distributed resources, increase distance between resources and load. And number 2 is called the operational factors. What are the operational factors? That is operational factors or operational factors boundaries. Greater transmission network complexity, aging infrastructure, and lack of expert and high power delivery. Okay. Then number 3, external influences or external boundaries. That is what we need to do it. So what it demonstrates, first, a legal and regulatory framework, integration of renewable energy resources, CO2 reduction, and energy efficiency. In order to deliver the result or to operate your power system within their operating boundaries, what we need to do? A complex grid structure required, a smart solution. Okay. Now, just a recap, we have also discussed in my lecture number 1 and 2 as well. What is basically a demonstrate of fundamental characteristic of a smart grid? What are the smart grid fundamental characteristics? First is self-healing. What do you mean by self-healing? The grid rapidly detects, analyzes, responds, and restores. That is important to understand. That is first key elements or key deliverables from the smart grid, self-healing. Number 2, empower and incorporates the consumers. That is the second elements of the smart grid. Ability to incorporate consumer equipment and behavior in grid design and operation. Number 3, tolerant of attack. Very important. Number 3 as well. Grid mitigates and resilient to physical and cyber attack. Number 4, provide a power quality delivery. Needed by the 21st centuries, users are based on CMBA curves. Grid provides a quality power consistent with consumers and industry needs. Number 5, accommodate a wide variety of supply and demand. That is very important, that you have a different type of demand and supplies as well. Grid accommodates variety of resources including demand, response, combined heat and power, wind, photovoltaic, and and use efficiency. So last year fully enabled and is supported by the competitive market. That is the last attempt from as far as the smart grid is concerned. So these are 6 deliverables must witness when we are going to implement a smart grid operation control challenges. Okay, technology options for a smart transmission system. Unused capacity. In order to utilize the maximum available capacity of transmission system, we have to use a different type of technology. So today we will discuss only a power electronics based FACS technology, and later on HVDC, and later stage we will discuss reactive power management, segmentation and grid shocks observers, energy storage, wide area monitoring, protection and control, synchrophases technology. Okay, now we are going to start reactive power compensations, FACS devices, as I discussed in my earlier slide. First, we will discuss first generations power compensators, and then we will also give highlights on second generations. Today we'll discuss first generations and second generation static power compensator thyristor based controllers. So that's a first generation's controllers here, and second generation compensator, and then a third generation compensator we will discuss on later stage. Today we will discuss first and second generation compensators. So first is a mechanical driven and second is a thyristor switched controls. Okay, on my next slide I will give you what we need to control by using the reactive power compensator. Okay, AC power transmission system technology concept. What basically it demonstrates here. Okay, controlling a power transfer parameters. What are the power transfer parameters? This is my generation or sending end, and this is my load or receiving end, and center is my line reactance or power. Okay, the parameters. These parameters are playing an integral role to deliver a power at its maximum levels in order to maintain seamless operations. Okay, if you can see here, the first is voltage magnitude, second a parameter of transmission line reactance, and third is a power angle. These are 3 parameters must be monitor servants in order to deliver a seamless operations, in order to deliver maximum power into network. Okay, on my next slide I'm going to demonstrate how these parameters are interlinked with a power system operation and what are the technology available. Today we'll discuss a mechanical, later on we will discuss a power electronics based transmission controllers. Okay, now I'm going to discuss in earlier slide discuss the power equations. So how these can be driven by mechanically. Okay, so if you can see here, and this is my voltage magnitude here, transmission line reactance, and power angle as I have discussed my earlier slide. Okay, it derived from generations, sending end voltage and load side or receiving end voltage and load angle, and this is my power being transmitted through the transmission network, and this is my line reactance. Okay, now so this power equations replicated with a power network. How it's replicated? Okay, if you can see, this is my generation side and this is my load side or receiving end. So this is my line impedance, this is my power, and this is my QR. Okay, now if you can see here, on middle is my power equations. Vs and Vr, receiving and sending end voltage, demonstrate that being voltage are compensated by using a switched capacitor and reactors for reactive war compensators. That is capacitive and reactive mode of operations. On the bottom here in phase are tape changers for transfer for the voltage regulations. Similarly, in the middle here we are using a series capacitor for line impedance control. Okay, on third parameter, sending and receiving end, load angle being controlled by quadrature tape changes are transfer for transmissions angle control here. So these are 4 devices are used to control voltage magnitude, transmission line reactance, and power angle to deliver maximum power and to maintain a seamless operation. Okay, now again here see controlling a power transfer parameters. So what is electric power transfer? P equation, that is power. First is a voltage magnitude, then a transmission line reactance and power angle. So this is my sending and this is my receiving end. This is my generation side, this is load side, and this is my line reactance and power here. Okay, now I will replicate with another my transmission network, but it's being controlled by other ways. Okay, now I'm going to discuss a power electronics based transmission network. Okay, now in the power transmission network here, power electronics based, again here this is my generation side or sending end, voltage and load angle. This is my receiving end or load side, voltage and load angle. This is my line reactance and this is my power. So this is my V or Q control, voltage and reactive power control. Okay, as we discussed first generation compensator, now we are going to discuss a second generation compensator, that is a power electronics based. Now same equations we will apply with a power electronics based devices. If you can see, the first here is my generation side and this is my load side, sending and receiving end, and this is my line reactance and this is my power here. Okay, what are the 3 key parameters I have to control? A power angle, line reactance and voltage magnitude. These are the viable key elements, key parameter in order to control and deliver a seamless operation. Okay, what I'm going to do by using a power electronics based devices, first if you can see, this is my generation side and this is my load side, and this is my line impedance, power, and this is my Q reactive power. Now if you can see, this is my equations, a power equation, Vs VR. In the center is a line reactance and last is a load angle. Okay, I'm controlling my Vs and VR, sending and receiving end voltage, by using a static VAR compensator. Okay, to improve a voltage, so I am using thyristor controlled voltage regulator, TCVR. Okay, again in the center here I'm using a thyristor control a series capacitor, that's a TCSC, in order to control the line impedance. Okay, this is my third device, and my 4 devices power electronics based is a thyristor control a phase angle regulator, that's a TCPAR. So these are 4 power electronics based devices are used in order to deliver a seamless operations and to maximize power delivery into the power transmission network. Okay, this is basically my thyristor switch. Now I will explain a little bit about the thyristor switch and then we'll conclude our today presentation, and later stage we'll discuss a third generation compensators. Okay, this is my thyristor switch. If you can see, very simple, but its operation is very complicated. Okay, thyristor switch semiconductor. Ideally, thyristor switch turn on when its voltage increases through 0 and firing control angle pulse is on. Okay. Second, turn off at the current 0 crossing. Number 3, it also alpha or delay angle firing angle control. It's also known as the control angle. Now I will demonstrate the current or voltage characteristic. If you see here, this is my y-axis and x-axis. If you can see here my x-axis, this is my forward current and this is my reverse current. This is my forward voltage and this is my reverse voltage. Okay, over here, if you can see here, this is my gate 0, gate 1, gate 2, gate 3. Okay, this is my gate 0 current here, and this is my gate 1 current here, and gate 2, and this is my gate 3 current here. So the Ig3 is greater than Ig2 and Ig2 is greater than Ig1. Okay, so this is my forward blocking and forward leakage current here. This is my forward blocking and this is my forward blocking leakage current here. Okay, so this is also called the here this is the on state here, and this is the reverse biased and this is the forward biased here. So this is my reverse breakdown voltage, and this is my forward based voltage, and this is called the knee here. So this is a breakover voltage. So this is the current voltage characteristic, how a one semiconductor can behave as far as voltage and current characteristics are concerned. Okay, now this is SVC, static VAR compensator. The composition of SVC, the first it demonstrate here the TCR, that is thyristor control reactor, and second is the TSC thyristor switch capacitor. So SVC are two main components. One is a reactor and second is a capacitors. Now from next slide we are going to discuss TCR and TCSC characteristics. Okay, if you can see here, this is my thyristor switch controlled reactors here. This is my thyristor switch here. This is my thyristor switch. Okay, now if you can see here, this is my system voltage in sinusoidal waves. Okay, and when my firing angle or alpha is on 90 degree, so I have the current here on 90 degree. So as soon as my alpha angle change from 90 degree to 120 degree, so then my over here firing angle delay angle is changed from 90 to 120 degree, and this is my inductor current, and this is the area is called the conduction angle, and then it will switched off and then switched on again, and this is switched off and then switched on again. So this is my sigma is my conduction angle, this is firing angle. So this is how thyristor switch control reactor voltage and current wave shapes. In my next slide here, okay, this is a TCR thyristor control reactors. First, if you can see here on right hand side is on my thyristor switch here. In the first waveform, voltage versus current, so it demonstrate here. So when the firing angle or delay angle was 90 degree, so the voltage and current was in sinusoidal waveform. In the second here, when the firing angle or alpha angle changed from 90 to 120, so your current waveform changed. So the further 180 and further the current waveform and your conduction angle also changed. Now if you can see on my right hand side, the harmonic content versus my firing angle, and red is my fundamental current here. Okay, now if we maintain a 90 degree, so there will be 11th and 7th and 5th harmonic content will be present there. So as the firing angle increase from 190 to 120, so it 11th and 7th reduced, and at 180 degree, it's eliminated or diminished. So 3-level quasi harmonic neutralized 48 pulse modulation is a good approach in order to eliminate the harmonic contents. Okay, now TCSC transit of free switching here. This is my again thyristor switched here. Okay, now if you can see here, this is my system voltage and this is my current here. So this is my VC or capacitor voltage. Basically, the switching control in the TCSC principle, once each capacitor is charged to either the positive or negative system a peak voltage, it is possible to switch any or all of capacitor on and off for any integral number of half cycle without transient. Okay, second here, if you can see here, so the capacitor is normally discharged after the TCSC is switched off. The maximum possible delay in the switched on of the TCSC one a full cycle of the applied voltage. As soon as this is TCSC switched on, so it will complete one complete cycle. So the current in the TCSC branch varies linearly with applied voltage according to the admittance of the capacitor. Secondly, the maximum applicable voltage and the corresponding current are limited by the rating of the TSC components, capacitor and thyristor wall. Thank you very much for your precious time. On my next lecture, we are going to discuss third generation compensator devices. Okay, conclusion. Controlling power transfer parameter. Today we will discuss mechanical driven switch transmission components and power electronics based transmission control devices. Okay, next topic, shunt and series compensator, that is third generation power electronics devices. Okay, these are references, the paper which I have published in different conferences and journals. Thank you very much for your precious time. Together, everyone achieve more. Please don't hesitate. Send me your feedback and comments. t.masood.dr@bath.edu. Please stay at home, safe, inspired and blessed. Thank you very much again for your precious time.